So I have four compounds listed here, and I have their boiling points listed too. So even though these compounds look similar, they all have a H4, their boiling points are different. So what's the reason? So we have to look at the structure first. So the structure for all of these are tetrahedral. Tetrahedral, if you remember, our structures are all nonpolar because they have no lone pairs. Therefore, they're nonpolar. So if they're nonpolar, and we're looking at intermolecular forces because that's what determines boiling points. Intermolecular forces, that means that these only have dispersion forces because dipole forces only happen when there are when they're polar molecules. So these are all nonpolar. But there's still a difference. Even though they're all dispersion forces, there's different strengths of dispersion forces, and that's caused by if you look at the pattern, these all go down a column in the periodic table. So if you go down that column, what happens? You're increasing molar mass. When you increase molar mass, you're also increasing the amount of electrons. So to illustrate that, if you have a few electrons on the outside, they can't move as much, and therefore their dispersion forces won't be as strong. But if you have two rings, right, two orbits, when the nucleus tries to pull in the outer electron, it doesn't have as much strength. So these electrons have more freedom to move. Therefore, they'll have stronger dispersion forces. And this concept is also polarizability. This is the concept of polarizability. And I have a video on that if you need more information on that. But over here, here's an example. I made up these electron numbers and these dispersion forces, but it's just to show you a point. So if you have you have a molecule, right, and you have these electrons. If you just have one ring, one orbit, what happens is these electrons don't have that much freedom to move. So even though these electrons try to repel each other, these electrons aren't going to move as much. And the point is, like, if you have these electrons pushing these electrons kind of, there's sometimes, even though there should be four, sometimes there might be 5 electrons because it's pushing against it. So the electrons are being pushed on this side. So if there's 5 electrons, that's going to give it an overall negative charge on this side and a positive charge on here, because it should be 4, and it turns out there'll only be 3. So it'll be a positive charge here and a negative charge here. Now if you have another molecule come along and it has the same thing, it has a negative and positive charge, that negative charge is going to be attracted to here, and that's intermolecular forces. That's what determines the states of matter. So the same thing here, right? But except there's 2 orbits. Now what happens is the outer ring has more freedom to move. So when it moves, more electrons will be on one side than on here because they can't move as much. So here the negative charge will be even stronger. It'll be -1. And over here, since even more electrons move to this side, there'll be less electrons here and then have a positive charge. So overall, what's happening here is that the size of the compound is getting bigger and bigger, and the bigger it gets, the more flexibility that the electrons have, and therefore the stronger the charge. The stronger the charge, the stronger these guys are going to stick to each other. And if they're really strong, you have to put in a lot of energy, and that's why the boiling points keep getting higher, because the stronger they are, the harder to pull apart, and therefore more energy. So you have to keep putting more and more energy to break apart, to boil from liquid to gas. So that's the reason why boiling points keep getting bigger. So overall, the trend is increasing molar mass, increase in boiling point.